Hey guys, I wanted to do a follow-up lesson to the one or to the different lessons we've had about writing names or naming ionic compounds. Um, what we've done so far is we've gone through and we've looked at if I give you a formula of an ionic compound, you should be able to name it. And just most recently, we talked about these polyatomic ions, which are groups of usually they're nonmetals, groups of nonmetals that we just name by one thing. So NO3 we just call nitrate, SO4 we call sulfate, um, and so forth. OH we call hydroxide when they're together like this. So um, we kind of went through and we did a bunch of examples going with just regular monoatomic ions like this one, where we just have one positive element and one negative element. And then we had some polyatomic ion examples. The question is, we have some of these with various numbers in the formulas, like why do I need a 2 on MgCl2, and why do I need 2 hydroxide ions, and where do these numbers come from? Well, if you remember when we first introduced ionic compounds, we said that when we first introduced the two different kinds of chemicals, we said that ionic compounds are when we have two oppositely charged ions that attract each other. Okay, so we always have a positive ion and a negative ion. Okay, so it really has to do with what charges are held by the ions that that helps us come up with these formulas. So let me mention a couple other things about ionic compounds, and I'll tell you how we can come up with formulas for them. Okay, so an ionic compound is basically the same thing as a salt. Like table salt is just one example of an ionic compound. An ionic compound is when we have a positive and negative ions that stick together. And contrary to what you may have learned in elementary school, where you may have just, kind of one positive and one negative just kind of sticking together, that's not at all what happens on a molecular level. Really what happens is if we have these positive ions, we'll say imagine are the green ones, and the negatives we'll imagine are the purple, just for argument. If you were to have a solid composed of ions, they wouldn't just stick together in pairs. They would actually bond in this huge network of ions together called a lattice. And we know from various microscopy and crystal structure that this is really what happens, that it's not just one or two ions, it's actually a huge network of ions. So you can kind of think about this whole thing as one big molecule containing billions or trillions of different ions. And you can see this is a very fine grains of salt zoomed in. You see it, they still hold the same sort of lattice structure. You can remember the word lattice because if you ever have had an apple pie, maybe with a crust on it with a certain zigzag. So a lattice crust on an apple pie is kind of the crust that goes like this. Well, a lattice is sort of the network of the crisscross pattern of ions sticking together. So coming up with a formula for this would be kind of difficult, right? Like every molecule, depending on how, or every chunk of a salt that you break apart would be different size and would have a different formula, right? Like imagine this chunk has 96 sodium ions and 96 chloride ions all stuck together. If I were to break it in half, would the formula be cut in half? I mean, it would get really confusing to do that. So the way we write formulas for all ionic compounds is we write what's called the empirical formula. We know that ions are going to stick together in a really large network of ions, but it doesn't matter how large the actual group of ions is. What we really care about is the ratios of the ions. So in other words, we really only care about something like sodium chloride. If there's 96 of each, that's really the same thing as a 1-to-1 ratio, right? For every sodium ion, there's a chloride ion. Okay, so I could call this a 1-to-1 ratio. And remember, just like in algebra, we don't like to write ones when we don't have to. Okay, so we would just call this NaCl. What this really means is that for every one sodium ion, there's one chloride ion. Okay? That's not the case because with every single ionic compound that's possible, because it may be that there are twice as many of one ion than another, or 3 times as many, or some other odd combination. Okay, so I wanted to explain how this works. So in order to come up with the ratios, we write what's called a subscript. We've mentioned subscript before. A subscript is a number that goes down below. Okay, so a subscript for any chemical formula, not just ionic compounds, but any chemical formula, tells you how many of that element is present. So for example, if I had a compound made of magnesium as the positive ions and fluoride as the negative ions, those are 2 different charges. Okay, so I'm going to have a ratio that's not going to be 1-to-1 because the positive charge and the negative charge aren't going to cancel each other out in that case. So I would end up needing a ratio of 1-to-2, and we'll get to that a little bit more. So I would magnesium fluoride, the only way to write magnesium fluoride's formula is MgF2 because I have twice as many fluoride ions in that formula. If I had magnesium ions and oxide ions, I'll kind of scroll so this isn't blocked. Magnesium ions and oxide ions, those both have the same charge. Okay, since these charges line up, I've got +2 and -2, I will have equal numbers of those. So my ratio would just be 1-to-1. I would call it MgO. So that's how I would write the formula for magnesium oxide. Remember, that's just the name of the positive ion and the name of the negative ion. Okay? So in case you're wondering where I'm getting these charges, these are on your periodic table. Now, I couldn't find a digital document of the one that I kind of hand drew for you in March. Or actually, that might have been at the end of February that I gave that to you. So I'm going to post this one. This is the one that I give all my juniors and seniors who are chemistry students. It has a little bit more information on it than we normally need, but it has the things on it that we will use, such as the charges. And it also has all the group numbers on here. I just have it scroll up. So 1, 2, 3, 4, 5. So the group numbers, that has the period numbers on there. There's lots of really helpful information on there. But the big thing that you'll be using for this class are the charges. Okay, so remember that when these elements become ions, these are the charges that they adopt. So lithium is a +1, sodium is a +1, potassium, rubidium. Some of them have more than one charge, like iron has a +3 or a +2. For this class, if you're not sure which charge to use, just use the first one. Okay, so whichever one is listed first is the most common charge. So if you're not sure which charge to use, just use the first one listed. Okay, so let's go through a couple examples, and I'll show you how we can kind of come up with any formula for any ionic compound. So I'll just show you a little bit at a time here. First thing to do, so if I just told you magnesium fluoride and I wanted you to write the formula, which I already gave you this as an example, but we'll figure it out. I would first write down what are the ions. So I'd look at the periodic table and I'd say, okay, magnesium ions are always +2 ions. And then I would say fluorine, so fluoride, fluorine ions are always a -1 ion. So I would write down an Mg +2 and an F -1. I know that those are my charges. And remember, you can just write a minus instead of a -1. Okay, so if you think about this a little bit, I'll move this up to the side. A +2 and a -1 are not going to line up, okay, because this is not balancing out. Instead, what I would need is an additional -1 charge, an additional fluoride ion to cancel out magnesium. So I've got a +2 and a -1, 2. So the ratio of magnesium and fluoride ions has to be, my mouse quit working here, has to be 2 fluoride ions to 1 magnesium ion. Because magnesium's charge is greater, it needs more negative ions to cancel it out. So the formula should be MgF2. I need 2 of those negative things because the charge is smaller. I need twice as many of them. Remember, this number down here isn't the charge, it's how many of them you need. Okay? When you're done writing the formula, there shouldn't be any charges left over. We haven't seen anything like that before, so you get rid of the charges after you've written the whole formula out. So magnesium chloride, so Mg, and I know that ion has got to be a +2. Chlorine is a -1. Okay, so I go -1. Okay, so you go through and you think about, well, I'm going to need twice as many chloride ions to cancel out the magnesium. So this is going to be really similar to the example, but I know my formula's got to be MgCl, and I'm going to need 2 chlorides. Zinc phosphide. Okay, I'll have to look these up. +2. Phosphide would just be phosphorus by itself, which is always a -3. So I've got a +2 and a -3. So this one's going to be a little bit tricky to do. So you think about this and you say, okay, we've got Zn and P -3. If I was to come up with a formula for this, if I had 2 zincs and 1 phosphorus, that would be a +4 and a -3. So that wouldn't work. If I had 3 zincs, that would be a +6. Maybe I could do 3 zincs and 2 phosphoruses. So that way I could do +2 times 3 would give me +6. So I could do Zn with a subscript of 3 there. And I could do phosphorus with a subscript of 2. What am I saying here? I'm saying that I would need 3 of these zinc ions. That would give me a total of +2, +4, +6 on the positive side, and 2 of these negative phosphorus ions. So I'd have -3, -6. So I'd have -6 and +6 only with this combination. Well, you look at how many I have, though, because remember the subscripts represent how many there are. So here I've got 3 zincs, so Zn3, and 2 phosphoruses, P2. So that's the only way this ratio is going to work. And you realize after you do this a few times that there's a certain pattern that's happening here. You can see it with the lithium where the 2 kind of came down from the sulfur, and with the calcium where the 2 went over there and the 3 went over. That what we're really doing is we're taking the charge on one ion and making it the subscript on the other ion. And what I call this is the crisscross method. So if you recognize this, that just the number, not the positive or the negative, usually ends up going to the other side. And remember, we usually don't write ones, but that's a good way to kind of shortcut your way to writing the formulas. If you can figure out the charges, you can usually figure out the formula pretty quickly. So your homework tonight is going to be basically just figuring out the formulas based on just the name. And remember, you have to look up the charges on a periodic table. Like lithium bromide, I have to look up on a periodic table. Lithium I see is a +1, and bromine is way over here as a -1. So I know that it's got to be Li has got to be a +1, and Br is a -1. So these are both the same charge, so that's going to be a 1-to-1 ratio. So my answer should be LiBr. Okay, I strongly suggest doing this step, at least on a piece of scratch paper or something, before you come up with the answer. I know a lot of you are just searching right on the internet, but if you actually want to learn this for your chemistry class, which you'll need to know this at some point, you gotta actually learn the rule on how to do this. Okay, so I'll post this tonight. I'll give you about a week to do it, and at some point we're going to have a naming and formulas little quiz. So it'd be better to have the rules down pat before we jump into that. Hope you all are doing well. We'll talk to you soon.